This video is going to show you guys how to evaluate logarithms. Logarithms were really created so that we could solve for exponents. You guys have never had an equation where your variable x or s or r or t, your variable has never actually been in the exponent. You might have had equations with exponents in them, but you were never solving for them. So that's what logarithms help you guys with. So if you're looking at 2 squared, we know that 2 squared equals 4, and we know that 2 cubed equals 8. But when you look at the expression 2 to what power equals 6, it's not going to be a perfect value. Now, I know how to solve for these, and I know that 2 to the power of 2.58 is going to give us the value 6. And we're going to learn how to solve for that exponent. So mathematicians define the x value using a logarithm, and they write it as x is going to equal log base 2 of x. So the way we go back and forth between solving logarithms is writing them from log form to exponential or exponential into log, and vice versa. So it says definition of a logarithm with base b. When you guys are trying to solve for an exponential form, it's going to start as a log. So it says log base b of y equals x. So when you're rewriting this, that means that that base of your log to the power of x equals y. So that's how you rewrite it. And there at the bottom it says the expression log base b of y is read as log base b of y. So when we're trying to solve for a logarithm, it says rewrite each in exponential form. So I'm going to do 2 and 4 with you guys, and I'm going to have you guys try 1 and 3. So number 2, that base of the log comes over, and we would write this, it goes from log to exponential form. So we write it in exponential form as 6 to the 0 power equals 1. Anything to the 0 power is 1. That's one of your exponent properties. So number 4, okay, same thing. 1/2 to the negative second power equals 4. Well, that would make sense because it would be 1 to the negative second over 2 to the negative second, and to make that positive, we would flip it. So it would become 2 to the positive second over 1. 2 squared is 4 over 1 is still 4. So go ahead and rewrite number 1 and 3, and when you're done, they should make sense with the expression that you've come up with. So logarithms of 1 and logarithms of b with base b. So what happens, guys, just like in number 2, anytime we have this log base b of 1, it equals 0 because anything to the 0 power is 1. Now the new thing that you guys may not know is that logarithm of base b with base b. So anytime the base of your log and the base, or the argument of the log, so the base and the big part, if they match, then it's going to equal 1, because what's going to happen is that you're going to need them to equal each other. The only way you can equal itself with an exponent is by taking it to the first power. So anytime you have a base b and an argument, or a big part b, it's going to equal 1, because that's the only way you're going to get it to equal itself. Now, the common log, guys, we use place values of 10. That's what we do. We don't use place values of 3s or 4s. We go 10s, 100s, thousands, 10,000s, and so forth. So, just like you guys know that x really equals x to the first, and square root x really equals, or has an index of 2, when you guys see this base, or when you don't see a base there, you guys have to know and assume and understand that that is always going to be base 10. And that's going to be important when you guys go to start solving these. So just like when you don't see a power, you know it's 1. When you don't see an index, you know it's 2. When you don't see a base, we know that it's base 10 for your log. Now the last thing here is this natural logarithm, which is ln. Natural log and that base e that we talked about, they're inverses of each other. So whenever you guys have them, in the same problem, they're going to cancel each other out. So log base e and ln cancel, and you're left with x equals x. So natural log is really a log base e. We're going to write it as e. So don't forget to try number 1 and 3. I'm going to flip over and do some examples with you guys. So when we're trying to evaluate these, again, we take the base of the log and we pull it over and it becomes the base for an exponent. So when we look at number 5 and it says log base 3 of 9 equals 2, we're going to pull that over and say, okay, 3 squared equals 9. So number 6, log base x of 8 equals 3. The x comes over, and we're going to say, okay, x cubed equals 8. So what cubed equals 8? X has to equal 2. Number 7, same thing. The base of that log comes over and becomes the base for our exponent of x. 4 to the x power equals 64. 4 to what power equals 64? We know that it's to the third power. So x would have to be 3. So the base of the log, that little subscript, comes over and becomes the base for the exponent. What was ever on the right becomes the exponent. So I'm going to try a couple of these with you guys. So let's look at number 9. Now number 9, remember, if we can't see it, that's a base of 10. So you don't have to, but I like to write this as equal to x because we're used to solving for something. So 10 to what power, or 10 to the x power, would equal 100. 10 to the second power. So I don't care if you write it as it just equals 2, or if you write the whole expression 10 to the second power equals 100. I'm just looking for that exponent though. So what about number 10? Again, we're bringing this over. So 5 to what power equals 1/5? Well, whenever you guys see a fraction and a whole number, so we're going from 5 to 1/5, or vice versa, if you're trying to go from 1/5 to 5. To flip between a whole number and a fraction, it's going from technically 5 over 1 to 1 over 5. So when something gets moved to the bottom of a fraction, remember our exponent rules say, oh, that must have had a negative value, a negative exponent. So, not thinking fraction right now, 5 to what power would equal 5? The first, but because it's now 1 over 5, that means that negative 1 power had to have been negative. So, 5 to the negative first power would equal 1/5. Number 12, same thing again, we can write this equal to x, or just equals what, but this 7 is going to come over. So we're going to say, okay, 7 to what power equals 7 to the 4x? Well, if they're both a base of 7, then this value has to be 4x. And that's what happens because your log base 7 and your 7 base for your exponent cancel out, and this will just equal 4x. And number 13, now like we said again, the natural log and the base e are inverses of each other. So anytime you have them in the same problem, guys, they always cancel each other out. So as soon as you see natural log base e, we're just left with 630. and 1. That is what your expression would simplify to. So go ahead, try number 8 and number 11. Now this one's not tricky, number 14. It gives you two functions, one that's exponential and one that is a log. So your g function is a log function, log base b of x. And your f function is b to the power of x, so that's our exponential. Now it says find f of g and g of f. So the first thing it wants us to do is plug the exponential, or I'm sorry, plug the log into the exponential. So f of g, we're going to plug the log base b of x, that's our g, into where our x is. So that actually becomes the exponent for b. So because our base of this whole exponent, log base b of x, is b, and the little base of our log is b, they're going to cancel, and this is going to equal x. Okay, what about g of f of x? So now it wants us to plug the exponential into the log. So we're going to start with log base b of x, but instead of x, we're putting b to the power of x, which is f. Well, same thing, log base b, exponential expression with base b, they cancel, and it's left with x. So what this is showing you guys is that these two expressions are inverses of one another. So log and exponential equations with the same bases are inverses of each other. So if you remember, when we did that verification by composition back in Unit 3 or Chapter 3, when they both equal x, it says, okay, these functions are inverses of each other. So when you guys go back and forth, they're going to keep going back and forth between log and exponential when you guys start to solve them and when you're trying to work with them. Now the last three problems in your notes are just good examples for simplifying. So I'm going to do number 15 with you guys, and I'm going to start number 14, then you guys are going to finish it. So 15. We can only cancel, guys, if these were both 5. Now, if I'm looking at 25, I'm thinking, okay, it's similar, but it's not 5. Now, we can rewrite 25 as 5 squared, if you guys agree, correct? So instead of 25, I'm going to write this as 5 squared to the x power. Now, when we do that, our exponent rules say that this will give us log base 5 of 5 to the 2x. That x gets multiplied in their power to a power. So now that our base of our log and the base of our exponent are the same, this expression just equals 2x. But you can only cancel if the bases are the same, the base of the log and the base of the exponent. So as long as they are, or you can manipulate it so that they are, they can cancel. So number 10, this is 10, or number 14, 10 to the power of log. Remember, if you can't see it, it's base 10. So 10 to the power of log base 10 of 4. So what happens there? What does that equal? And then go ahead and do number 16. And let me know if you guys need help with anything.